Good afternoon, class. Today is September 23rd, and this is the lecture for September 24th. And it is on optical lithography. So before we get started, I went into campus this morning and got a semiconductor wafer. This is a silicon wafer. So you know, you can sort of see what's going on here. And you know, it's so shiny and the features are hard to see, but okay, here we go. All right, so you can see the features on it basically. This wafer, oh, I remember what this is. Okay, so yeah, this is a CMOS switching wafer, and so this wafer consists of somewhere around I don't know, maybe 30 to 40 steps, and you know, somewhere around 20 layers of material. And so at each step you basically perform lithography to produce a lateral pattern on the surface. And it's, as you'll see, it's sort of akin to photography. Litho stands for, I mean, defining a feature, I think, and graphy, you know, well, it's like photography in a sense. And so you know, today we'll go through how you produce those features on the surface. And I'm going to try and, you know, not use the projector here. I have the textbook here. We are in the chapter on optical lithography, which basically in the syllabus, the whole chapter is required reading. And it's interesting to me teaching this because I first did optical lithography without it being taught to me. And it's sort of like you go into the clean room and someone shows you how to use the machine and do things, and then you just sort of start learning. And so most of the time doing this, you sort of learn as you go. So, but I can convey a few tips here. It might be a short lecture because, you know, there's only so much you need to know. So let's take our wafer, all right, and what we're going to start with is contact lithography. And you have the video, the clean room video that shows NAM actually doing this. And so, you know, that's a lot better than my pictures here. But you start with photoresist. And there's a device called a spinner, where there's a vacuum port. I mean, basically it kind of looks like this, where there's a vacuum hole in the middle that goes down, and that eventually goes to a vacuum pump that produces a vacuum there. And usually the way these things are arranged is there's a little controller there. Probably in NAM's video, you know, it'll show him putting the wafer down on the vacuum chuck. And so putting the wafer down, and then pressing a button or flipping a switch to cause that some valve to open up, and so the vacuum holds it down. Now, what's going on here is that there's sort of some mechanics in there that allows this thing to spin while it's under vacuum, and so the vacuum holds the wafer while you spin. Now, therein itself lies a lot of stuff you will need to learn. I mean, just about things like the vacuum chuck. There's different kinds of vacuum trucks. I drew one here that just has a little hole, and of course that would be good for smaller wafers. For bigger wafers, you'll want a bigger vacuum chuck to hold on to it, and so immediately you're faced with the decision, of what type of vacuum chuck to use. The vacuum can cause the wafer to bow. There's lots of considerations. But the main thing you want is when you spin this wafer in the spinner at usually anywhere like a few thousand rounds per minute. It's usually the speed parameter is RPM, rounds per minute. So for example, if it was 2,000 rounds per minute, it would go around 2,000 times in 1 minute. So it's really spinning. And the main thing is you don't want the wafer coming off. So your choice of vacuum chuck can be kind of important here, because sometimes you're putting a wafer on, for example, if I was, doing step number, 23 on this, I wouldn't want this to go flying off the chuck and get destroyed after putting that much time and investment into it. All right, so assuming you've chosen the right chuck and you put the spinner, you then drip some photoresist. So you use a pipette, and you use that pipette to withdraw some photoresist from a vial, and then you basically drip some photoresist on the wafer. Now, even stuff like that, there's things to learn, because you kind of ideally want the photoresist to drip all the way around. You don't want to put down a pattern with your dripping that leaves like a hole in the middle, because you're trying to make a coating by spinning it, and so it's moving outward to the edges of the wafer, and so if you don't want a situation where after spinning you're left with kind of a gap in there. And so there's actually, there can be, depending on the size of the wafer or the shape of the piece you're working on, there can be a little bit of, thought as to even how you put your drip pattern down on the wafer. And additionally, frequently you program a spinning recipe that starts kind of slowly, and the idea is that you have some drippage here, and then you run it kind of slow so it spreads the photoresist out, and then you do it fast to give you your thickness. And so typical thicknesses, so then you're left with a photoresist layer. And it can be anywhere from, a tenth of a micron to 10 microns thick. And that depends on what you're using the photoresist for. And there's a nice, there's a few equations here that are useful to note. The thickness, T, is proportional to 1 over the square root, and I'm going to write RPM, just so you know that's the spinning speed, and usually that's how you're given. So now it's also proportional, as it says in the book, to the viscosity. You choose different resists for different thicknesses that you might require for whatever step you're doing. we sort of talked about liftoff and you know, the thickness there needs to be thicker than the metal you're putting down, things like that. We'll get back to that when we do recipes. But basically, for a particular resist, you can adjust the thickness a little bit by choosing different speeds. So if you want a little bit thinner, you spin a little bit faster. Now, and he kind of has some you know, discussion in here about that, the spin process. Now, okay, we'll do this in order. I was going to talk about positive and negative resist, but we can you know, proceed with our. So you know, that's sort of step one, is to spin the resist, and then step two is to do what's called a pre-bake. Now, he talks about, oh, by the way, yeah, I mean, he talks in here about you can put down a layer of an adhesion layer, a polymer adhesion layer, to make the photoresist stick better. I personally rarely did that, but that would be what he's describing there, this stuff called HMDS, which is basically a vapor. You set up a little vapor chamber and you put your wafer in there so it gets this coating of the material that makes it sticky. Yeah, pre-exposure bake. So pre-bake before you do anything. Now, what that is primarily for is to drive the solvent out of the resist. Meaning, when you take this liquid, this photoresist, and you put it down on your wafer and you spin it, as spun on the wafer, it contains solvent, because it had solvent in it originally. Basically, photoresist is some photoactive chemical that would be too thick by itself, and so you mix it with a little bit of solvent to make it flow better. And you don't want that solvent after, you know, on your sample when you go into exposure. So now, what did he put in here? The pre-exposure bake, 90 degrees centigrade for 30 minutes in an oven, or 90 degrees. Okay, so I would never do a pre-bake for 30 minutes. Basically, it typically might take, you know, 90 degrees Celsius for 30 seconds. And in fact, usually you do that on a hot plate because you can kind of see you can see the wafer basically as you do the pre-bake. It'll change reflectance, the color of the reflectance as the solvent evaporates out of it. And in all these bakes, there always is a discussion of hot plates versus ovens. An oven basically is a little box that's, you know, like an oven, and whereas a hot plate is basically a hot surface. And you know, I guess I don't want to get into the complications of choosing to do bakes in ovens versus hot plates at this point in time. Okay, and so then the next step is you then do your alignment. And remember, this is contact lithography, and so this is done in a mask aligner. And there's a nice picture, figure 9.5. Basically, you have your wafer, and you put it on a chuck in the machine. This is a vacuum chuck. And you have your photoresist. All right. And then you have your mask. And I should have brought a photo mask, but there is a nice picture of one here in the preceding chapter in figure 8.8. It's basically a glass plate with metal patterns on it. Now, first problem, determining what side of the photo mask the metal is on. Because obviously you want that close to the wafer because you're going to be shining UV light, ultraviolet light, through the mask, and you want the metal to block the ultraviolet where you don't want it to go. And so if you accidentally flipped it the other way, the metal would be up here and it would spread around and it wouldn't give you a sharp pattern. And in fact, he goes into some discussion here. Sorry, in the wrong chapter. He goes into some discussion here about how close the figure 9.9, he talks about how close the wafer needs to be. And he gives you an equation here. I've never seen this equation, but basically that equation is a function of the gap and the resist thickness. So the minimum feature okay, okay, so let me get it right. So I should have made some room. The separation between the photomask and the wafer is G, and that's the equation. Just a second, I gotta get a piece of chalk. And the resist thickness, he uses D, yes. And he gives you an equation there which, you know, the minimum feature is proportional to the square root of G plus D over 2. Which sounds about right. And usually usually G is larger, much larger than D, but sometimes not. So you can remember that equation. That's useful to know. So you may be asking yourself, well, why do you have any separation at all? And okay, so in the mask aligner, ideally it's what it says. You bring the mask into contact with the surface of the wafer. So why might you not? Well, okay. One reason is because when you spin photoresist, you're going to get a bead at the edge. All right, and so that prevents the mask from getting closer. Another reasons are the wafer itself could be bowed, you know, not perfectly flat. So there's a variety of reasons why there's going to be some gap. Ideally, it's 0. What you do in the mask aligner is you put your vacuum you put your mask in your mask holder, and then there's a little knob where you start moving the vacuum chuck up, and you feel when it gets into contact, it's like getting harder to turn up, and it doesn't happen often, but every once in a while, if you crank it up too hard, it cracks the wafer, especially if you're doing some fragile material like indium phosphide. But anyway, so the idea is you get it pretty close, and ideally, if you're trying to make, you know, say 10 micron features, all right, you want both G and D to be much smaller than 10 microns, which is kind of clear. All right, so once you, okay, well, actually, I talked about contact. and you do that. You bring the wafer into contact, and then you separate it a little bit. Okay, so A, bring into contact. Then B, you lower it a small distance. All right, so this wafer chuck is on a stage and you can raise and lower it. So you bring it up into contact and then you bring it down a little bit. All right, and the reason why you do that is because you're going to now do your alignment, which is that, okay, let's say you have a wafer, and let's say you've already put down features, okay, like that, from a previous step. And your photo mask has, so I need colored chalk, but let me try and draw my photo mask. Let's say my photo mask has a feature. I'll draw it off to the side here. So this is your wafer, and this is your mask. And say your mask, your next step has features like this. All right, and those features are meant to line up with these features. So you back it off a little bit, and then the chuck has three movements. It has X and Y, of course, and it also has rotation. So you do all three things, and because you might have another set of features over here, all right, where I'm just drawing something, okay, and they're supposed to line up with those features. And so you can kind of get the idea that, okay, if the wafer is rotated wrong, it's not going to line up. And so, you know, I'm drawing it side by side, but obviously this is on top of that. You lower the chuck into the board the way I have it drawn, and then you can move it up and down and also rotate it. And in fact, what I've drawn here are, you know, and we're sort of jumping ahead, and we keep having to mix in recipes. Often your first step in any recipe fabricating a semiconductor device is to put down what's called alignment marks. So with a bare wafer, you might do an evaporation step, like liftoff, where you're putting down markers on the wafer. They're called alignment marks. All right, and they provide the sort of the registration for the rest of the steps. So all the rest of the steps, each mask is a different step, has marks that are supposed to line up there. And in fact, what I've drawn here is, I mean, kind of a very rough alignment mark. This is sometimes used. This is the actually usually it's sort of a plus sign and then 4 squares like that. And so you would line things up. And then this mask might have, you know, some sort of device features that are your next step. And basically every photolithography step, you have a different mask. I mean, sometimes if you're making small things, you can have the same mask and use different areas of it. But easier to think about it, that each step has a different mask. And so each mask would have the alignment marks for lining up with the original alignment features that you put on the wafer, which are typically just some metal features you put down. And there's actually a lot of, he talks about alignment marks in here, I believe. Well, he talks about alignment, no. Okay. Alignment marks, okay, yeah, and 9.4. So, you know, he talks about them. He doesn't give any examples. There are things called verniers, which are basically a set of lines in either direction and things like that. There's a whole art form as to how to make your alignment marks that result in two things. You can think about this, okay, if these are my alignment marks, meaning those squares are supposed to go outside of those. All right, well that's kind of easy. I mean, I can see them, I can line through and line them up. But there are other forms of alignment marks that, number one, kind of make it easier for the operator to perform alignment, and number two, result in more precise alignment because you have to do it more carefully to get it right. Now, okay, in real life, then the next step, once you have it lined up, and ideally, okay, then once you have your wafer lined up, you just bring it up and back into contact, and then you do your exposure, and it's exposed properly to make your features wherever you want them properly aligned with the rest of the steps. In practice, what often happens is that when you bring it up, it moves sideways a little bit because the machine is skewed or the wafer's bowed slightly. And so this tends to kind of go back and forth a little bit before you get it right sometimes. And sometimes it turns into a trick where you lower it a little bit and you actually line it up you misalign it on purpose because you know when you bring it back up into contact it's going to slide in a certain direction, and so you sort of plan for that. That's not typically the case when you're doing wafers, but it is typically the case when you're processing on little small pieces of semiconductor. All right, so step 3 is the alignment, and then step 4 is the exposure. Okay, so in step 4, it's brought into alignment. You shine light, UV light. Typically, the wavelengths he gives them in here. Will be well, in the ultraviolet, so somewhere around 300 nanometers, and there's different wavelengths that you can use, but oh, here we go. Under resolution, 365 nanometers is the usual wavelength that's used, but it could be a little bit toward the blue. So it's ultraviolet, and now that's sort of backing off from that. The photoresist, wherever it gets exposed by ultraviolet light, undergoes a chemical change that either causes it to do something different in the developer than the part that's not been exposed, and that's positive and negative resist, which we'll talk about in a little bit. But I merely want to point out that all of this is done in what's called the lithography room, which is under sort of usually yellow light, because if there was any white light, meaning including blue, it would expose the photoresist. And so it's sort of just like a dark room in photography. You have red light because the chemical material here is not sensitive to the red, and so that allows you to see what's going on. And usually you can get away with yellow, meaning as long as the lights don't have any wavelengths shorter than around 500 nanometers, it won't damage the photoresist. So you do the exposure now, and then after the exposure, all right. Now here there are some people that like to do another bake after this, but it's not typical. Usually after exposure, you go straight to development, but I'm just saying as an aside that some people explore recipes where they put another heating step here, but typically it's in the developer, which is, I mean, basically it's usually a beaker, and you have your, and usually what you do is, at least what I always did, was you use a basket with holes in it, and your wafer sits at the bottom there. So you have this basket that you can put your wafer in that you can lower into the developer. And even that turns into an art form, because when you place it in the developer, okay, you don't want any bubbles to form on the surface or anything like that. And so there's actually kind of, you learn techniques for lowering it in such that the developer sheets across it and nicely forms a nice total liquid coverage. Now, these things, and he has a discussion in here called process latitude, which, and he shows this figure here, which is that, okay, so for example, you might expose for 60 seconds, okay? And that might result in a development time, meaning a time to take, the time to remove the photoresist from the part you don't want it, depending on negative or positive, of say 60 seconds. Okay? So that can be your process recipe: 60 seconds exposure, 60 seconds development. Now, okay, so process latitude means, okay, what happens if you make a mistake? What happens if you accidentally expose for 80 seconds? All right, well, what's going to happen is that your development time is roughly going to go down to 40 seconds or something like that. It's not, I don't want to give the impression it's linear like that. But, you know, since you exposed longer, the development time is going to be shorter. All right, and that's called process latitude. It means, you know, how big of a mistake you can make that you can correct for in the subsequent step. And he has sort of a plot there of you know, what happens is that you quickly find out, for whatever photoresist you're using and the type of process you're doing, how important it is to get an exact number on either of these things. But basically, if you overexpose, you correct it. Now, the thing is that number one, what'll happen, okay, if this is the proper design for the process and you accidentally expose too long, it'll develop faster. And what happens is that your features can get too big, okay, because your development goes too fast. Now, what you find basically is that, okay, there are designed recipes for any photoresist. Whatever photoresist you're using, it will come with a proper recipe. Now the thing is that is for a particular exposed light strength, and sometimes your particular mask aligner has slightly different intensity of light, and so you need to explore a little bit and find out what works best to get the features that you want. And in fact, you may explore varying the exposure time and, you know, varying the developer time then, in order to, you know, maximize or optimize your results in terms of the sharpness of the features that you get. And then you rinse. And that itself, okay, so if this is the developer, you then have another beaker here, which is in water. Now, of course, this is deionized water. And even that can be an art form in terms of, like, what I would usually want to do is use a basket. A lot of people like, and I think that's what Nam did, he held the wafer with like tweezers and placed it in the developer, and then he would sort of watch it, you know, to see when the development finished, and then he would lift it out and put it in, or sometimes even take it out and put it in running DI water. And you know, you sort of work out what you're most comfortable with, but what you don't want to have happen is that when you remove it from the developer, it dries out, because that'll leave a film of material. So however you do it, when you pull it out of the developer, you want a bead of developer still on the surface before you either put it in running water or in your beaker of deionized water. And then you have your feature, and finally there's drawing. I'm going sideways here. Now, after you pull the wafer out of however you washed it off, you have to dry it off. That can be an art form, okay? And typically that's done with, as Niam shows with a blower of nitrogen air. Usually you want nitrogen because you don't want oxygen blowing on your surface. And I noticed Niam used this the technique that I always use, because if you think about it, your wafer comes out and it's wet on both sides, and so and it's kind of too difficult to hold the wafer and blow on both sides. And so what I would always do is you'd have clean room cloth, paper or something, and you would put the wafer down on it, and then you would blow on the surface, and you would blow, blowing the water off to the side, so that you remove it from the wafer, and then the backside is still wet, and then you sort of blow at the edge, and that causes the wafer to kind of fly up and down a little bit and dry off underneath as well. And so I think it's always best to avoid having to actually hold the wafer with tweezers if you can get away with it. And so drawing itself can be a step. Now, then you're done. For example, if you are doing liftoff or something like that, where the resistance is there simply to block something like the metal that's coming down or something like that. But an optional step then is 8, a post bake. Now he talks about post bakes in here, and I think he does. Hard bake. Yeah, he tends to write not in linear order. So you go back a little bit, and he has this section on hard bake in 9.1. That's actually kind of a critical step sometimes. So I'm going to erase a few things here. So here you are with your wafer now. All right, and you say you have some features in your photoresist. So that's photoresist. And through this whole process, you've created openings in the photoresist where you want them to be for whatever step you're performing next. And if that step is, for example, liftoff, you pretty much are done there. You put it in the evaporator, you deposit metal. I guess this is big enough to see. So for liftoff, and I'll zoom in a little bit. Okay, so here's your photoresist. And you deposit metal, okay, and the evaporator is vertical. So when you deposit metal in the evaporator, it goes everywhere, including on top of the photoresist and your holes where you want it, where you want your contact. And then the idea is then you put it in a solvent this way. which is typically acetone. And so you want the photoresist to be thicker than the metal you're depositing, so that it leaves this space for, because you're putting it in this beaker of acetone then, for that acetone to dissolve away the photoresist and lift off the metal, except for the metal in the hole. And the lift-off process. Now, you could never do lift-off on this, and so lift-off tends to be used more for research-grade devices or smaller devices. Because if you think about it, I mean, you're asking to put this in an acetone beaker, and over the entire wafer, you want that to be happening. See, I should have brought a smaller wafer, like a 3-inch wafer. This is a 12-inch wafer. And if everything has worked perfectly, what will happen is that in liftoff, all right, here's your holes, for example. So that's where you want your metal to be, and then everywhere else is photoresist. And when it dissolves in the acetone, all the metal here, not in the holes, actually, I mean, ideally comes up as one sheet that you can actually hold up with tweezers and look through, and you can look through the holes that you just made. Rarely does it work that well. And in fact, what usually happens is that you have to agitate like an ultrasound in order to get that photoresist to dissolve. But anyway, getting back to 8 here. All right. I'll put wavy lines under here because it's optional. If you're doing liftoff, you don't do step 8. Once you dry the sample, you put it in the evaporator and you do your deposition. And the reason why is because the photoresist is just there mechanically. It's not resisting anything. It's just being there. And in fact, you want it to dissolve very readily. You want it to be very chemically unresistive, so to speak, so that the liftoff process. So you don't do step 8 for liftoff. But if you're, for example, doing an etching process, which is the next subject in our class, and that's where, okay, here's my photoresist again. And now what I want to do is I want to etch. Okay, and I'm sort of drawing etching schematically there. Etching can be putting in an acid bath. That's the next chapter basically. With the idea that, after you put it in the acid bath or you put it in the plasma etcher, you create an etched feature here in the opening. Now, if you're doing an etch process where you're with a photoresist stencil, now the word resist means something. Where did I erase resist? Because this has to resist that acid or whatever it is you're using. It can't itself be susceptible to the etching process. And so then frequently for etching, you would do a post-bake. Now, the post-bake, what it does is it does what's called cross-linking. Which I don't want you to worry about that too much, but it just makes the photoresist makes it harder. I'll put that in quotes. It sort of it takes all the polymers inside there and makes them link with each other and make it more resistive to chemicals like acid etches that you might use. Now this step So I put in parentheses etch and that. So you may or may not doing it depending on what you're using the photoresist for. Okay, so now if you do post bake, you want to do it very carefully because you want to heat up enough to cause cross-linking, but you don't want to heat up so much because even if you do etching, I mean, you eventually have to remove that photoresist, which is in acetone. And so if you post bake at too high a temperature or too long, it won't be soluble anymore. And so you won't be able to remove it after you do whatever step. So post baking has to be done very carefully according to whatever recipe has been supplied by the photoresist maker. Finally, I'll do it over here. Positive resist. So as I started, I drew that the wrong way for what I'm drawing over here. That would be metal everywhere except openings. All right, so let's imagine my mask is like that, which is where there's openings that the UV light comes through. And so what I've been drawing here is for positive resist. That is, that's where the UV got through. And so wherever the UV got through, according to my photo mask, that photoresist goes away in the developer. That's positive resist. And negative resist, it's the opposite. Then wherever has been exposed stays in the developer. So it's just the opposite. Either the UV causes the photoresist to become soluble in the developer, or the photoresist is already soluble in the developer, and by exposing it, you make it insoluble. Insoluble? Not sure. And so you get positive and negative. Now, we've already seen that there's various reasons why you might do positive and negative resist. Negative resists tend to have more process development, and so they are used frequently just for that reason. Positive resist it kind of makes more sense to you, right? Now, there's two things though where, because of your process, you might use one or the other. And if you think about it, kind of what happens, because this part is getting removed, what can happen is that for positive resist, that hole may become slightly bigger than your feature on the mask, because you sort of expose it out and you develop a larger hole. All right. Whereas over here, actually, with negative resist, if that happens, if it develops laterally a little bit, it actually makes the photoresist feature smaller. So it's sort of like that picture I showed on E-beam in the last lecture. Negative resist, you can employ that to give you actually finer features. So you can work with that a little bit. Let me see what I'm up to here. Okay, and so it's positive and negative. Now in the book he also talks about the fact that for a positive resist, it will tend to give you this open V shape. All right. Whereas for a negative resist, because the light can go sideways, it'll give you an inverted taper. So you can also, if you do it now, if you think about it, this is very nice for liftoff, because if I make a liftoff feature with negative resist, ideally that's what I want. Because then when I deposit my metal, it'll go here, and it'll go here, and it'll be shadowed and go here, leaving the entire photoresist side surface exposed for my solvent. Now, very rarely does that actually happen, but ideally you can design that to happen. That's called an inverted taper, and so for liftoff it's particularly desirable. So it's, you know, to a certain extent true what he shows in figure 9.10. You can get different sidewall profiles with negative and positive resist, sort of inherently. And you know, the last thing here, photoresist stripping, is usually done in acetone. If you, it must be removed. It's always acetone. I mean, I guess there are other methods. See, this is where he's jumping back and forth ahead. Just for now, just you use acetone. Okay, that's how you strip the resist. There can also be plasma processes, but we haven't covered plasma processes, so just consider that it's going to be acetone. All right, so this is contact lithography, and what I'm going to do here is I'm going to keep my picture over there. And yeah, that's contact lithography. It's what it sounds like. It's where the photomask is brought into contact with the wafer. And contact lithography is usually used for like research grade or things like that, smaller features. It's not used in Intel because if you think about it, it'd be ridiculous for them to have to go through this step of, you know, bringing into contact and everything. And so there's also the projection. Lithography. And that's where, okay, and he sort of draws it in the book kind of wrong, but you get the idea. Just, there's an optical system that results in light going through your photomask, which in this case, I guess it depends on the optical system whether the features are, you know, which side they're on. All right, and that optical system is actually fairly complicated because you want to design it right so that when the light passes through, so here's my wafer with my photoresist. The idea is that usually there's a demagnification step so that the photomask is bigger, and so this, you know, light and dark features gets translated into sort of, you know, demagnified onto the surface like that. And in between there's a lens always that's bringing the light into focus. And I just remembered there's one thing I forgot to talk about, well, okay, we can go on here. So this is a projection system, and it's like, you know, any projection system, like the projector I use to project things on the board. You design an optical system to take some sort of light and dark pattern, like produced by a photomask, and project that with magnification or not onto a surface. And there's only a couple things, I mean, I want you to realize about that just as a general principle, okay? And it's about optics. And basically, the first principle is, okay, he doesn't use the words, I won't use the words either. If you have some sort of lens system, all right, and, you know, people draw focus like that, you know, coming to a point. That's not actually what happens, okay? Light undergoes, no, I draw it right. Light undergoes a narrowing, still can't draw it right. I'll make my lens bigger. So I'll do my light field first. Okay. So here's my lens, and here's what's called my beam waist. And so, you know, your wafer is here somewhere. You brought it down to the focus. All right, so let me draw another picture. Okay, with the same lens, but now with a longer focal distance. All right, and so I don't even want to teach you the optical terminology. If you're interested, you can look it up. There's things called numerical aperture and stuff like that. But the point is that if you design your optical system such that the distance from the lens to the wafer is small, all right, you can get a very tight beam waist. All right. If it's large, the features are larger. Okay, and this is this equation he uses in here, resolution. Oops, sorry, I drew it the other way around. Oh no, this is right. Okay. All right, so you can get a tighter focus. And it sort of just makes sense because if you think about it, you can get a tighter focus, but there's also something called the depth of focus. DOF here stands for depth of focus. And if you get a tighter focus, the Z distance, the depth over which it's in focus, will be smaller than if you have a wider focus. And so there's a trade-off here because if you think about it, if this distance is small, you have to be very careful in your placement of the semiconductor wafer, and you can even run into, you know, where, you know, places, you know, actual foundries are at the point where the topography and the wafer bowing itself, which is, you know, microns, impact the depth of focus, and so they have to do a trade-off here between tighter focus and longer depth of focus because of imperfections in the topography and bowing of the wafer. So I wanted you to be aware of that aspect of things. And he doesn't really have the same picture here, but he sort of refers to it. And then finally, so the principle that DOF is proportional to 1 over, and I guess we'll use the term resolution. I don't like the term resolution. I'm going to use the word line width. Meaning you can design your optical system, that's the other way around. Resolution is the right way. Okay, so let's do it that way because resolution is kind of a funny term. You don't know what it means, but line width, okay, that's the size of your feature in the wafer. And so you can design it for a small feature, but then your depth of focus is also small. So your precision in the wafer flatness has to be greater. Or you can design your optical system for a larger line width and get a larger depth of focus. And so there's this engineering trade-off, and basically this is the result of mixing equations 10.1 and 10.2. I'll go over this more in the chat session tomorrow. And finally, I'm going to erase this. I wanted you to be aware. So why do I want you to be aware of this? Well, okay, it's not because you're going to be using projectional lithography in your graduate studies or even perhaps in your career. I mean, most people do contact lithography their whole career if they're making semiconductor devices. But if you go to a place like Intel or some place like that, you'll need to understand, you know, at least these terms and some of the optical principles. And so that's what I'm going to get across to you. So one, line width, or do it the other way, depth of focus, portion of the line width. And number two, I want you to understand, and this is section 10.6.1, phase shift masks. And it's a very nice picture there that basically, I guess the masks are upside down. If your mask has two openings like this, all right, for the light to get through, on your wafer, your exposure will look, you know, like this. Meaning those two features kind of blur together a little bit. Now, a phase shift mask is a neat thing because basically you make your mask with those openings, but you've designed on this one a layer of dielectric glass such that the light coming out here is 180 degrees out of phase. Now, I mean, okay, so here, you know, you have to, you know, it's like the projection system. How much optics do you already know and how much can I teach you in a few minutes? Everyone knows that light is a wave. And so everyone knows that that you can cause a delay in the light, and you do that by introducing a dielectric there. Now, this is the intensity, and what happens with the phase shift mask is that if you draw the electric field here, it looks like that. All right. On this side, because it's flipped at 180 degrees, the electric field is the opposite. And so when the intensity, which is E squared, okay, those cancel. It's an interference phenomenon basically. Where they come together, they cancel each other out, and so your intensity then gives you nice sharp features. And that's phase shift masks. And you get the idea that when you design your mask, okay, with openings next to each other, there can be a very complicated algorithm for what openings you would put that phase shift in. But I just wanted you to understand the principle. And that's it for today. So we'll have the chat class tomorrow and go from there.